Hi everyone, welcome to the session. So let's solve this very interesting interview question. This is a very common circuit for analog designers, but here the the problem is very interesting. Okay, so let's solve it. So this is a 5 transistor OTA. You all know 5 transistor OTA, and we need to find what is the small signal gain. That is nothing but our V out over V in small signal. Okay. So this is the circuit. So let's see what is the DC bias condition of this circuit. Okay. So we can paste it. So in DC bias, what will be the picture? So here this is AC small signal. So this will be deactivated. Okay. So it will be short circuited, right? So it will be grounded. So what do you think? Like is this circuit is biased properly? Biased properly or not? What do you think? So we can see that this is the ideal ideal current source. Okay, but as there was present a small signal voltage source, so this will be short circuited, so this potential becomes now ground. Okay, right? So this will be zero potential. Now what do you think, what will be the VGS? So to make all the transistor in biased, your VGS must be greater than VTN, right? So let's say the VTN is 0.5 volt here, and our V bias is, let's say, sufficient to make this all the MOSFET in saturation. Okay, now let's say, okay, so this is 0 volt. Let's say our VDD is 5 volt and our V bias is, let's say, 3 volt. Okay, so how do you think? So here we can see the VGS becomes 3 volt. Okay, right? So it is properly in, like, it is the turning on condition, and we can see this can be biased properly. Okay, and this current has to be flows through that branch as the ideal current source having any voltage across it. Okay, ideally, right? So here this ideal current source is, like, this is the ideal current source. So if the voltage across it is 0 volt, so there is nothing, no problem for this current source. Okay, so like, we are somehow managed to make the all transistor in remaining saturation. Okay, so this whole circuit is biased properly. Okay, right? So now see the small signal picture. So actually, so there should be some I naught by 2 current, and there should be I naught by 2 current. Okay, and this is I naught. Okay, so now somehow we make this make all the MOSFET in saturation. Now we will see what is the small signal behavior. Okay, so we will be trying to solve by 2-3 methods. Okay, so now in AC small signal, how will be the VD? So this will be short circuited. So it will be AC ground, right? So this will be grounded. And here the V bias is the DC potential. So this will be grounded as well. And this will be short circuited to the ground as well. Okay. So this is 0 volt small signal. So this is 0 volt small signal. This is also 0 volt. This is 0 volt. And here small signal, this current source will be open circuit. So this will be like that. Okay. Now we have only a V in here, and we have to measure what is the V output here. We are assuming M1 and M2 are identical. Okay, M1 and M2 are identical, and M3 and M4 is also identical. Okay, okay. Now what do you think? How can we solve this? So let me do the small signal analysis first by drawing the small signal parameters. And for the easy calculation, I am neglecting channel modulation of input pair. Okay, so GDS on 2 is 0. That is implies RDS on 2 is infinity. Okay, now if I draw the small signal, so it will be looking like that. So this is a small signal current. This is GM3 Vx, where the Vx node is here, and here we have, and we have RDS of P. Okay, RDS of P. Similarly, we have a same current source, that is, this current is nothing but GM. Okay, so let me write as GMP here. Okay, GMP and GMP. So this will be GMP. What will be the V out? So it will be connected here. So this will be GMP VX as well. Okay, and here will be another output impedance of this MOSFET 4. So this is another RDS of P. Okay, now here we have connected. So here we have small signal V in, right? So this current is going downward. This will be nothing but, so this is 0 volt. This is 0 volt, and this current is GMN times. What do you think? What is the VGS here? So VGS is nothing but minus V in. Okay, right? The gate is grounded 0 volt, and our VS is nothing but V in. So this will be minus. So this current is minus GMN V in, and this same current will be same, right? So this will be GMN times minus of V in. Okay, so this is the small signal parameters, small signal model. So this is 0 volt, and here we have V output. Now we need to solve this KCL and KVL. Okay, so let me do that. Then I will tell some another technique how we can comment easily for the small signal gain. Okay, so now how do you think? So this same current has to be flow there, right? This is a single series path. Okay, so in the series path, the current is same, right? So we can directly write the expression like the following. It will be, so this current is nothing but, upward current is nothing but GMN Vx will be equal to, okay, GMN V in will be equal to, so this current plus this current, right? So this will be GMP Vx plus Vx minus 0 volt. So this is small signal ground. So this will be nothing but Vx itself divided by RDS of P. Okay. So let's say this is the equation 1. Similarly, we will write the expression for this for this branch as well. Okay, for this branch as well. So similarly, we can write GMN times V in equal to GMP Vx plus V out over RDS of P. Okay, so these are two similar. So we need to just remove that Vx in any expression. Okay, so from the first expression, I can write Vx is taken common, so it will be GMP plus 1 by RDSP equal GMN times V in. Now from here I can write Vx is nothing but uh, so this will be GMN V in times GMN divided by GMP plus 1 by RDS of P. Okay, so let me be write that. Okay, now we need to put this Vx to that expression. Okay, to this expression. Now from here I can write as well. So GMP V in GMN V in will be equal to GMP Vx. So now we need to replace that Vx, right? This Vx, okay, this Vx with this. So this will be V in GMN by GMP plus 1 over RDS of P plus this will be V out divided by RDSP, right? V out divided by RDS of P. Okay, so this is the final expression we need to solve. Okay, as a form of V out over V. So I can take common. So this will be V in is taken common. So this will be GMN minus GMP times GMN divided by GMP plus 1 by RDSP, right? V out by RDS of P. Now if I do the further calculation, we will get V out by V in. So it will be so I am taken here. So it will be RDS times this value. Okay, so GMN minus GMP GMP plus 1 by RDSP, right? RDS of P here. Okay, so now assume some small assumptions. Okay, so this is the small signal gain. Okay, so this is the final expression we have. We have this final expression. Now let's take GMP equals GMN. Okay, now how do you think what will be the case? So this expression, let's say this is AV, so this is small signally, this is AV. Okay, voltage gain will be equal to that. So we can put here, so this will be what? So it will be RDS of P GM minus GM square by GM plus 1 by RDS. Okay, RDS of P. Now if I do further calculation, it will be nothing but, so let me do this, RDS of P will be equal to GM square, so it will be like GM plus 1 by RDS of P. So this will be GM square plus GM by RDS of P minus GM square, right? Now we can see this cancels, and we are having only and this also cancels, right? This and this. So we will be having GM by GM plus 1 by RDS of P. Now further if we calculate that, it will be GM RDS of P by 1 plus GM RDS of P. So this is the calculations. Okay, let me check if I did something wrong or not. Okay, calculation wise. Okay, so let me do that. So from here the Vx is nothing but it will be GMP plus 1 plus RDS will be equal to GMV in, and our Vx is GMV in divided by GMP plus 1 plus RDS. Yes, okay. So now we have to check GMV in equal to GMP Vx. So GMP and Vx is nothing but that term plus V out by that. Yes, okay. Now if I can take common, so this will be GMN minus GMP GMN divided by yes, this is okay, and this is okay. Now this is nothing but the multiplication of this two sided will be like that. Yes, it is okay. Now if I take GMN equal to GMP equal to GM, okay, equal to GM, so it will be RDS. Yes, okay, it is okay. So it will be GM square plus GM by RDS of P minus GM square, okay, divided by GM plus 1 plus RDS of P. Okay, so it will be GM. Okay, from here I can write GM RDS of P divided by GM plus 1 by RDS of P. Okay, so if I take from here okay, no, so this is the final expression. Okay, now if RDS is tends to infinity, what do you think what will be the gain? So gain will be around equal to 0, right? 0 gain, right? Or not? No, it is not 0. So it is going to be, let's say, GM RDS of P is very greater than 1. So what do you think what will be the, so gain is around 1, right? Now let me see what is the intuitive analysis of the circuit. So this was our circuit. Let me copy this. So you can see, so so there will be same current will be flowing through that branch and that branch as well, right? And that two, sum of these two current is nothing but that current. Okay, now if we can make, so what do you think, what is the voltage here from here to here? So it will be nothing but a common gate, right? So the gain will be nothing but these GM times that are out looking from here, right? Looking from here. So now from, so let's say this is the Vx. So Vx is nothing but, so this will be plus GMN times the looking in impedance from here. So this will be nothing but 1 over GMP, right? This is a diode connected load. So this will be 1 over GMP. Now from here to here, from here to here, what is again? So gain is nothing but this GM times the R out present here. Okay. So now, so let's say V out will be nothing but, so there is a common source configuration of the PMOS, right? So this will be a negative sign. So this will be GMP times the R out. So this will be RDS of P, right? Because we are assuming this transistor having infinite output impedance. Okay. Into Vx. Okay. So V out is nothing but GMP into RDS of P into GMN into 1 over GMP. Okay, so we can see this cancels, right? So we are having minus of RDS of P into GMN. So the gain from that branch, from here to there is that. Now what about this path? So this path is also having some gain, right? So we can see this is also a common gate. So how do you think, what will be the gain from here to there? So here this V out from the, this from that branch, is nothing but GMN times the RDS of that node, right? So this will be RDS of P, and this will be only a plus because this is a zero phase shift, right? From common, for a common gate application and topology. So now, so we need to add these two paths, okay, so that we can get the final output. So this is a V out 2 and let's say this is V out 1. So if I do that, V out equal to V out 1 plus V out 2. So what do you think? So V out 1 is minus of RDSP GMN minus RDS of P into GMN plus this GMN into RDS. So this will be GMN times RDS. So you can see it is getting a 0, right? 0 gain. Right? So this was the gain. So it will be Vx. It will be V in, okay? So here will be V in as well, okay? Because this is the output voltage, not the gain. So now we can see, so V out by V in is 0, okay? Now, so this is the final answer, okay? So previously what we are getting by solving some KCLs and KVLs, we are getting this type of equation, but I think this is this should be equal to almost 0, okay? Okay, let me check here. GMV in equal to GMPVX plus, okay, so let's write that version as 1 over GMP parallel RDS, okay? We can write that this term, okay, this term we can write that. So from here we can also write that Vx by 1 by GMP parallel RDS. Okay, so this will be Vx by equal to, so gm v in. Okay, now here Vx equal to V in GMN times 1 over GMP parallel RDS, right? Now if I put here GMVX, so Vx is V in GMN times 1 by GMP parallel RDS of P. From here GMN minus GMP GMN 1 by GMP parallel GMN. So from here V out over V in is nothing but RDS of, okay, now we can assume the GMP by RDS of P. Okay, so we know that RDS P is very greater than 1 over GMP. Okay, so this term can be evaluated to 1 over GMP, right? So RDS of P into GMN minus GMP GMN into 1 by GMP, right? Because the parallel combination of GMP 1 over GMP parallel RDS of P will get 1 over GMP. So this cancels. Yes. So now this is expression is coming. So we can see the gain from here RDS is nothing but GMP minus GMN minus GMN, right? So this is 0. So eventually the gain is 0. Okay, so this is the correct expression. So what I have mistakenly done, I don't know. Okay, so I think so previously the calculation was wrong. Okay, so please forget it. Okay, forget it, and this is the final calculation. Okay, so eventually if you do the small signal calculation, the gain is almost 0, right? You can see that. And so this is the intuitive analysis. Another intuitive analysis is the following. Okay, so let me share it. So okay, let me do this. So this circuit can be, okay, so here if I make this to be ground, AC small signal ground. Now what is the VGS here? So previously the VGS was minus V, right? So now if I make, so the VGS can be V in if the V gate is 0 and VS is positive V in, that is on condition. And another condition can be VG is V in but the VS is 0 volt, right? So now make this node ground and this node as minus V. Okay. Okay. So let me, the VG can be minus V in, right? So let this is minus V in small signally and this is also minus V in. So the VGS remains minus V in as previously, right? As our previous condition. Okay. Previously the VGS was also minus V. Okay. So now what do you think? So this becomes a common mode signal, right? For this two node, this is a common mode signal. So how do you think for a common mode, what is the common mode gain of a differential or the 5 transistor OTA? So this is almost 0, right? So common mode signal is applied. Signal is applied. So you can think of there is a common mode signal of minus V in of these two node. So we know the 5 transistor OTA having a almost 0 gain. for a common mode input, right? So eventually the gain we can directly common V out over V in is almost 0. Okay, so this is the another take a look into this picture, like this is the another look, so that we can comment on the gain. Okay, so there are three solutions I have been discussing. On a small signal approach, you can write some KCL and KVLs, and okay, and then you can arrive at V out over V in expression, and you can comment on the gain. Okay, then I have shown two paths. There is two signal path from V in to V out. One is from here to here, and another from here to here, and then the two gain should be added, or the V output voltage should be added, so that we can get the final output. Again, similarly, we can use this model as a common mode signal of minus V in, then we can directly comment the gain will be almost equal to 0. Okay, ideally. So thank you everyone.